Uh, Good evening to all. Welcome to the fifth week tutorial session of NPTEL course NOC25-me113 Power Plant Engineering. My name is Ananthakrishnan. I do this problem solving session as part of my PMRF TA duty. I'm a Ph.D. candidate from Department of Mechanical Engineering, IIT Delhi. So in this week, we will see the continuation from last week. Till last week, we have seen steam turbines. This week around, from this week onwards, we'll look into hydro turbines and hydroelectric power plants. So we can move into the multiple choice questions and the numericals that I have set for this this tutorial session. The first MCQ, look into it, and I'll also try to solve it. Look into the first problem. The power output from hydroelectric power plants depends on depends on three parameters: head, type of dam, and discharge. Head, discharge, and efficiency of the system. Efficiency of the system, type of draft tube, and type of turbine used, type of dam, discharge, and type of catchment area. Obviously, efficiency of the system should be a part. So anything that has to deal with the power output has to have some kind of efficiency associated with it, depending upon blade efficiency or blade or vane efficiency or some other mechanical efficiency or any kind of efficiency that is involved in the process. There can be frictional losses in between. That efficiency will have to be taken into account. So the first part, the last part, the efficiency of the system is a must. So then we have to look into the other parts, head and discharge. Obviously, head and discharge are correlated to each other. A higher head means higher discharge. So certain type of turbines need higher head, like the impulse turbines require higher heads compared to the reaction turbines, where pressure is also a part which produces power in addition to the head of the head required for the turbine. So head, discharge, and efficiency, all the three are considered while calculating the power output from the hydroelectric power plants. Type of dam? No, I don't think so. So because ultimately the only thing that has to take into account is head only. And that will take into consideration the height of the dam and whether it's an arch type dam or the vertical flat type dam doesn't have any kind of effect on the power produced from the hydroelectric power plants. The type of trap tube, type of turbine, not that much in terms of the power output because the draft tube type can only only do this much, change the velocity at the outlet that is required to prevent the discharge directly into ambient pressure, where the output pressure in case of most of the turbines will be lower than that of the atmospheric pressure. So to discharge it to the ambient, you need to have some kind of a diffuser or an increasing procession that is attended. That is something called a drafting. Type of dam, discharge, type of catchment area, no. So basically, the answer to this problem is option B. Uh, Now we can move into the second problem. Uh, look into it. It's based on turbines. Francis, Kaplan, and propeller turbines fall under the category of impulse turbine, reaction turbine, impulse reaction combine, and axial flow. Which out of the three options are right? Right, right. So the answer to this problem is reaction turbine. Basically, a reaction turbine operates based on Newton's third law of motion. It makes use of both the kinetic energy that is obtained from the height from which the water comes from, and also the pressure energy of a fluid as it flows through the turbine blades. As the fluid passes through the turbine, it expands and the pressure decreases, causing the turbine blade to rotate. So basically, reaction turbine, the Francis, Kaplan, and propeller turbines fall under the category of reaction turbine, where Kaplan turbine uh, um, it's basically based on how the fluid exits a turbine, whether it flows in axial or in radial direction. So that will be the differentiation factor between these two turbines. Propeller turbines, these are the counterparts of axial fans, where the flow happens from axial inwards to axial outwards. So basically, all the three were not just the impulse or the impact of the fluid, but also the drop in pressure throughout that will be converted to the power. So the answer is reaction turbine. So I'll note it down. It operates on it uses both kinetic energy and pressure energy. As the fluid flows through the turbine, it expands. And its pressure decreases. Uh, this this results in the rotation of elements. Now we can move into a small numerical based on the prototype and model speeds, runner speeds. A hydro turbine is required to give 25 megawatt at 50-meter head and 90 RPM runner speed. The laboratory facilities available permit a testing of a 20 kilowatt model at 5-meter head. What should the model runner speed and model to prototype scale ratio be? You can do it and try to solve it. I'll also try to solve within a minute. How will we tackle this problem? There is a prototype and there is a model. So what should be the comparison parameter that should be kept as a constant? The dimensionless parameter that should be kept as a constant, so that a similar comparison can be one-to-one comparison can be made between the runner, between the prototype as well as the model. So what should be that parameter be? Dimensionless parameter. Yes, I'm asking what should be the dimensionless parameter that should be used to compare the prototype and model, so that an equivalent comparison can be made to identify some parameters that are not available for either prototype or model. So you can't actually do the testing for all the type of prototype in similar environmental conditions. So what we do is that we make a model of it and use some dimensionless parameter to bring an equivalence to of the equivalence between the model and the prototype. So the final results of the model using equivalent parameters should simulate a similar performance of prototype. So some kind of comparison has to be made, or some kind of an equivalent parameter has to be established before you do the test for the model. So in the case of a prototype and a model, in the case of hydroturbines, that dimensionless parameter that brings an equivalence between the model and prototype is called the specific set. So it could be established as a dimensionless parameter that takes into consideration the speed at which the turbine or the model or the prototype rotates, turbine rotates, the power which it consumes, and the head associated with the fluid flow. So these three parameters are the most critical ones. And these three parameters can be coupled to bring a dimensionless parameter called a specific speed. Yes, right. It's a specific speed ns. Yeah. So if you know the value of ns of a model, it should be the same for the prototype as well. So once you get that, if you do not know one of the power, either of power or head or the speed of one model or prototype, and if you know everything else, every other parameters, all the other five parameters, then you can actually determine it quite easily by using this specific speed. Uh, so, so have you tried to solve this? Did anyone get the answer? What should be the unit? RPM. Well, can it cross verify it once again? So I'll try to solve it. So I don't think it's the right answer. So I'll try to solve it. Give me a second. I just need to make a small bit. Okay. So I'll try to solve it. Sorry, slight issue with my system. So I'll start solving it right now. Sorry. We need to actually determine the model runner speed. The specific speed is the equivalent parameter. Can write the prototype specific speed. N as prototype, that is equal to the RPM of the prototype, root of the power divided by the head raised to 5 by 4. Everything is of the prototype. Here the power will be in terms of kilowatt. N will be in terms of uh, RPM, and H will be head in terms of meter. So when we substitute it, N root P divided by H raised to 5 by 4. N is for the prototype, it is 90 RPM. So this is 90 RPM. And the power in terms of kilowatt will be 25 into 10 cube kilowatt RPM. And the head will be in terms of meters, it will be 50 meters raised to 5 by 4. So the specific speed that is an equivalent parameter between the prototype and the model, that is equal to 107. And now we have to compare between the specific speed as well as of prototype and the model. The specific speed of prototype will be same as specific speed of model. So 107 will be equal to, similarly, n root p divided by h raised to 5 by 4 for the uh, model. N root p divided by h raised to 5 by 4 for the model. So this will be equal to n will be for the model, it will be, we have to determine the n of model. Power will be 20 kilowatt divided by height h of 5 meters. Therefore, model speed will be equal to, solving this, it will be equal to 35 divided by 20. It will be 178.89 RPM. So the second part could not be solved because there was not sufficient data for the dimensions, related dimensions of problem. So that was a mistake from my part. This will give the model runner speed. You have to compare the specific speed for the model and prototype and determine the quantity that is not available from the other 5 quantities. So this problem has 5 parameters given, and you can calculate the 6th one using this comparison. Look into another numerical. It's slightly more tricky. I'll read through it. A Pelton wheel is receiving water from penstock with a gross head of 510 meters. One third of the gross head is lost in friction in the penstock. The rate of flow through the nozzle fitted at the end of the penstock is 2.2 meter cube per second. The angle of deflection of the jet is 165 degree. Take CV, coefficient of velocity as 1, and the speed ratio of 0.45. Determine the horsepower given by the water to the runner and the hydraulic efficiency of the Pelton wheel. So it's a Pelton wheel where only the impulse will be considered. There is no reaction as such from the pressure. Determine the power by the water to the runner and the hydraulic efficiency of the Pelton wheel. How will you tackle this problem? I'll give you a minute to look into it and formulate it, and I'll also try to start after drawing the velocity variables. I hope you had the opportunity to look into the problem. I'll try to solve it right now. The question is regarding a Pelton wheel. So Pelton wheel is an impulse. Pelton wheel is one kind of an impulse turbine. So where the impact of the fluid coming from the nozzle is what drives the turbine. So we try to draw a blade, and the blade angle is given as 165 degree. Or this one, this angle is 165 degree. And can consider this as the inlet triangle, inlet portion, and this is the outlet. The angle of the deflection of the jet is 165 degrees. So what comes goes by 165 degree, and it's considered a pelted wheel is receiving water from a pen stove with a gross head of 510 meters. One third of the gross head is lost in friction in the pen stove, and the rate of the flow through the nozzle fitted at the end of the pen stove is 2.2. The volume flow rate is given. The angle of deflection of the jet is 165. CV as 1 and speed ratio of 0.45. These are critical, and then we have to determine the power. So in the case of Pelton turbine, what we could see is that the fluid flows in this direction straight and splits, and using the splitter, it will be uh, redirected like this. So if you try to draw in the triangle, the C1 will be the same as the wall component of the velocity. There is no axial component. And then if you consider relative velocity, you need to take into consideration the blade velocity. So if this is the blade component, CB, the rest will be the relative velocity, CR1. So this is, though this is a straight line, this is actually the inlet velocity considerations. Similarly, we have to draw the outlet velocity triangle. That will be a pure triangle. So what we do, there will be a relative velocity component, and then that will be CR2. So that will be at 165 degree from the incoming direction. So it will be deflected back, right? So that's why this, and then there will be the blade velocity component CP2, and then the axial velocity uh, C C2, and the ball component of this one will be this one. So this will be CW2, and the vertical component that will be the CF2. That is the axial, the radial component, or the axial component. Yeah. So once we have established the velocity triangle, we'll try to solve it. The problem is very straightforward. Given the quantities which are given are given head will be equal to 510 meters. Head loss in friction HF will be equal to H by 3. That will be given as 1/3 of the total head. So that is a lowest factor. That will be equal to 170 meters. Therefore, the actual net height that is available at actual head H will be equal to HG gross head HG minus HF. So that will be equal to 340 meters. So that will be the actual head that is available for power production. Then given angle of deflection is equal to 165 degree. Then so we need to actually determine what will be the angle. This is a total angle of deflection once. So we need to determine the blade angle from this angle of deflection. So this will be 180 minus. So you have to draw it a bit more straight in a straight manner. Yeah, this is better. So this is the blade angle. So we can denote it by phi. Therefore, the blade angle, phi is equal to 180. So the schematic or the letters? Oh, right. Let me just complete this. That will be equal to 15 degree. So this is the blade velocity component, and this is the relative velocity component of the inlet. So the actual velocity C1 will be the same as that of the world velocity component. So the world component CF will be the flow component. Of the actual velocity components of C1. So this will be the inlet velocity not exactly triangle, it's a straight line. So the outlet, there is a deflection of 165 degrees. Therefore, the blade angle will be uh, 15 degree. So this will be the relative velocity CR2 at the outlet. The blade component will be CB2, the blade velocity CB2, and this will be the actual velocity at the exit C2. So the actual velocity will be having a couple of components. The first component will be the world component CW2 and the flow component CF2. I hope this is big enough. And then the coefficient of velocity CV is 1 and speed ratio is 0.45. So I'll discuss this as and when we require this while solving the problems. What are these two components and where exactly are they used? So now we have drawn the schematic. Then we need to find the actual velocity. We do not have any information regarding uh, the velocity in the problem. We only have the head, gross head that is available and the friction losses. So the net actual head we have determined. So root of 2gh by the conversion of head to velocity can be one way in which we can get the velocity at the exit of a nozzle or the actual velocity at the inlet of the blade. So there is a coefficient of discharge that is associated, coefficient of velocity that is associated with it. So we here, since that coefficient of velocity Cv is equal to 1, we can take it straight away. So actual velocity at the inlet Cv1 will be coefficient of velocity and the root of 2gh. This is 1 root of 2 into 9.81 into the head net head. So that will be equal to 340. So that gives the actual velocity at the inlet, that is 81.67 meter per second. So one part we have obtained, that one of the most important part of the problem we have obtained, that is the inlet velocity. The question states we have to determine the total power. So usually in these kind of things, you have to determine the world component of the velocities to determine the power. So just calculating the actual velocity is not enough. Once you calculate C1, we move forward to determine the world component of the velocity. Uh, for that, we need the blade velocity component. So as you could see, uh, in the outlet triangle, the relative velocity and the blade velocity will give the actual velocity component. And we know the angle, vertical angle. So the horizontal component of the relative velocity in the outlet velocity triangle, CR, that will be a combination of the wall component of the actual velocity and the blade velocity component. So there is a speed ratio that is given. So we have to take that into account as well to get the actual velocity at the outlet and the world component of the velocity at the outlet. At the inlet, it's straightforward. The world component will be same as that of the inlet actual velocity. So C1 will be the same as the C1 will be the same as CW1, the world component. And we calculate the blade velocity or the velocity of the wheel. That will be equal to the speed ratio. Just like the previous case where we have used the coefficient of velocity, we use this root of 2gh into speed ratio to get the blade velocity component. And this C blade velocity will be same at the inlet and the exit, since nothing else is given. Since this is a Pelton wheel, we need not consider about the diameter variation that will be there at the inlet and the outlet to calculate the average velocity. So here we can directly take everything falls at the same diameter from the center. So we can actually take it to be the same. So if you try to observe with the velocity triangle, you might wonder the inlet and outlet will be at the same. So this is a vertical plane. Water hits at the center point, goes out. So the whole blade, this cross section will be at the same diameter away from the center of the blade, center of the turbine. So speed ratio is 0.45 given the problem. And you have to multiply by root of 2g. It's the same thing as what the previous case. So once you get it, so quite straightforward. So the value is 36.75 meter per second. Then the inlet, this is the inlet part. Inlet. So the relative velocity at the inlet CV1 CR1 will be equal to, as you could see in the inlet portion, CR1 will be equal to CW1 of C1 minus CB. C1 minus CB. So 81.67 minus 36.75. So the answer will be 44.92 meter per second. So that's kind of done. So it's a straightforward thing. That's a inlet part. Now we have to move into the outlet velocity triangle. From the outlet velocity triangle, the relative velocity, since the only thing that connects the inlet and the outlet apart from the blade angle is the inlet and the outlet relative velocities. Since no friction factor is associated with respect to the inlet and the outlet of the blade, so you can take the relative velocity at the inlet, CR1 will be same as the relative velocity at the outlet. No friction factor, no friction, hence CR1 will be equal to CR2. That will be equal to the given velocity 44.92 meter per second. So the next part we have to determine the whole component of the velocity CW2. So we know that will be equal to CR2 cos phi minus of CB2. The world velocity at the exit, world velocity component at the outlet, CW2 will be equal to CR2 cos phi minus CB. CR2 cos phi will be equal to 44.92 cos 15. 165 is the deflection angle, which makes 15 degree to be the blade angle. So minus of CB we have determined that will be equal to 36.75. That will be equal to 6.64 meter per second. That is a world component of the velocity. So now we know the inlet world component and the outlet world component. So power work done on the jet will be quite same. So we have to determine the first part of the problem. Power given by the water to the runner. How will you calculate the power? So you need to have force and the velocity. So velocity part will be the same. That is a blade velocity. How will you calculate the force? Force can be determined from the world velocity component and the mass flow rate of the water that impedes the jet. So mass flow rate of water multiplied by the changing velocity. Since it changes its direction, the relative velocity will be adding up the velocity. The absolute magnitude of the velocity will get added up. So CW1 plus CW2 into mass flow rate of water multiplied by the blade velocity will give the power given by the water to the runner. So this is equal to rho into flow rate into CW1 plus CW2 into C blade velocity. So if you put 1000 into the flow rate is given as 2.2 meter cube per second. So you can write straight away standard units. CW1 is given 81.67. The whole recalculated CW2 is given 6.64 into blade velocity. That is also calculated at 7.67. So the answer to this problem is 739.8 kilowatt. Second part, we have to determine the hydraulic efficiency of the turbine. That's also straightforward. So the blade efficiency will be equal to, it's also straightforward. So this is basically the power divided by kinetic energy of the inlet stream coming from the nozzle. So that will be uh, rho Q dot into CW1 plus CW2 into C plate into half into rho Q dot into C1 square. That is the actual velocity at the inlet. Just cancel the rho Q dot. That's the mass flow rate. That will give C2 into CW1 plus CW2 into C plate divided by C1 square. So substituting the components, we already know CW1, CW2, C plate, and C1 squared. So the answer will come to around 97.3%. So that solves the problem. It's a straightforward problem where you have to draw the velocity triangles at the inlet and the outlet and calculate the world component of the velocity. Once you calculate the world component of the velocity, we just subtract it or add the magnitudes to get the and multiply with the velocity of the blade as well as the mass flow rate of the water to get the power. Hydraulic efficiency, you have to divide this power with the inlet kinetic energy. That will give the efficiency of 97.3%. So if no doubts are there, we can actually move to the next problem. Look into the fifth problem and try to formulate it, and I'll also try to solve within a limit. So this numerical is based on Francis turbine. Francis turbine is a reaction turbine actually. So it has an overall efficiency of 76% and is required to produce 150 kilowatt. It's working under a head of 8 meters. The peripheral velocity equal to 0.25 into root of 2gh. And the radial velocity of the flow at the inlet is 0.95 times root of 2gh. The wheel runs at 150 RPM. The turbine's hydraulic losses are 20% of the available energy. Assuming radial discharge, determine the guide plate angle, the wheel angle at the inlet, the diameter of the wheel at the inlet, and the width of the wheel at the inlet. Basically, you have to calculate the flow rate, and from the flow rate, you can, and if you know the inlet velocity, you can get the area. So the area will be having couple of components, diameter and the width of the wheel at the inlet. And we have to determine the guide blade angle and the wheel angle at the inlet. So basically, the angle at which the velocity, the fluid impinges the jet, and the blade's angle. So these four are the parameters that we have to determine from the current problem. So as like in the previous problem, even though this is reaction turbine, we follow the same approach as that of the Pelton turbine or the impulse turbine. So we have to draw the velocity triangle and determine which all parameters are available and which all parameters are needed to be calculated to solve the problem. Uh, Unlike the impulse turbine, Pelton turbine, this is quite different. There is an angle at which the fluid impinges. This is the inlet velocity. Uh, and consider this to be alpha, the nozzle angle. Similar to the nozzle angle, it's a guide blade angle. C1 at an angle of alpha. And then there is the blade angle, C blade. And then there is this relative velocity, CR1. And there is theta, that is the guide blade angle. And then there is CF1, the flow velocity component. And we can denote it by CB, CR1, and the whirl component will be the horizontal component of the axial velocity. That is the inlet velocity triangle. In case of output, so this will be, this is a Francis turbine. It's a radial flow turbine. It will be purely radial at the outlet. So that is one thing that you have to keep in mind, especially for the radial turbine and Francis in nature. So that is the difference from the normal reaction turbines. So here, that is a radial or the relative velocity by the blade angle theta at the outlet by uh, and C plate to CF2 will be same as C. The flow velocity component at the outlet will be same as C2. So for the Francis turbine, note you have to consider The wall component at the outlet will be equal to 0. That's why this will be perfectly 90 degree. So CW2 will be equal to 0 for the Francis turbine. So that actually solves quite a lot of our issues, because in order to calculate the power, we need only the inlet wall component. So once the velocity triangle is formulated, we need to solve it step by step. So the discharge at the outlet will be purely radial, and hence the wall component will be equal to 0 at the outlet for the Francis turbine. So here the overall efficiency, it overall is given as 76%. The shaft power produced is 150 kilowatt. And the head equal to head is equal to 8 meters. So now we have to determine quite a lot of things. We have to determine the blade velocity component using the peripheral velocity, that is basically the blade velocity, and the radial velocity of the flow at the inlet. We have to determine the flow component, that is given as a ratio with respect to the with respect to the inlet velocity given as root of 2g. So the factor is 0.95. So we get CF1 from the second ratio, from this ratio, and C blade velocity from this ratio. And turbine hydraulic process are also given. And these are also part. So that also needs to be accounted while calculating the actual velocities. Blade over peripheral velocity, C blade is equal to 0.25 times root of 2gh, and the radial velocity of the flow at inlet equal to X1 equal to 0.95 times root of 2gh. So these two components are already given in this problem. And the wheel speed is given as 150 RPM. C discharge is purely radial at the outlet, so CW2 will be equal to 0 and CF2 will be equal to C2. I'm just noting down the things which are given in the program. Hydraulic losses are 20 percentage of available energy. So basically we have almost everything. The head is given as 8 meters. The peripheral velocity, blade velocity can calculate straight away. Radial velocity can calculate at the inlet. We can calculate straight away. That is CF1 we can calculate straight away. Uh, the blade velocity that will be equal to 0.25 times root of 2 into 9.81 into 8, that is 3.13 meter per second. And the axial, the radial component that they inlet, that is given as 0.95 times root of, yeah, head loss component is there. So we have to take that into account quite after sometimes. So the actual hydraulic efficiency is given. So we need to determine the the world component at the inlet using that. So in the hydraulic efficiency, uh, the total head at the inlet and the hydraulic losses how to be taken into account, as well as uh, the efficiency parameters. So what I'll try to do is I'll calculate this first and then determine the world component at the inlet from the hydraulic efficiency that is given in the graph. So there is a head available at the inlet, and then there is a turbine hydraulic losses. So the actual head is kind of different from the head losses or the friction losses that we have obtained in the case of Pelton turbine. So in the Pelton turbine, the head at the exit of the nozzle will be equal to the actual head, the gross head minus the friction losses. So that is corresponding to the pipe losses before entering the turbine. This hydraulic loss in the case of Francis turbine is within the turbine. It has got nothing to do with what happens before it enters the turbine, the space between the turbines. So this is quite straightforward. The head available at the inlet is 8 meters, so we need not do anything on that part. So we can calculate the blade velocity and the flow velocity component straight away. So that will be equal to 11.9 meter per second. So these two we got. Now we have to determine, as we have told, the world component of the velocity. So how will you calculate it? The hydraulic efficiency uh, is equal to total turbine hydraulic loss is 20%. So hydraulic efficiency will be equal to 80%. 80%, that will be equal to actual head for power to head at the inlet. So this is not something that takes into account the friction uh, of the nozzle or the pipe that delivers water to the turbine. So this is what happens within the turbine, the head at the inlet. So this is head inlet minus hydraulic losses uh, minus head at inlet. This is 1 minus 20% of the head at. So that's why this is 0.8. That's why we got this as 80%. This is the calculation. So once you get this hydraulic efficiency as 0.8, now we have to determine how to couple it with uh, the the world component of the velocity, and then the world component of the velocity and the blade velocity, and similar other parameters that are available in the problem. So what we have to determine? We got this one, hydraulic efficiency, which is nothing but the normal efficiency, equal to the power produced, the shaft power produced to the kinetic energy that is available at the inlet of the turbine. So that is how we determine it. So in the previous problem also we have determined the same quantity at the end, as 97.3%. So here it is just 80%. So this will be power divided by the head at the inlet. So this power in hydraulic efficiency doesn't take into account the mechanical losses due to the shaft friction, the friction that is encoded in the shaft. So this hydraulic efficiency is a pure form of efficiency that doesn't take into account the mechanical losses. So basically, power is we have simplified the problem for the Francis turbine with CW2 axial component to be 0. So CW1 into C plate into the velocity plate into mass flow rate. So divided by mass flow rate into head available into GH, head at the inlet. So we can calculate it. So that will be equal to the world compound of the velocity is something that we have to determine from the problem. C blade we have already calculated as 3.13 and the head is 8 meters. So we can determine this is equal to point 8. So we can determine CW1, the axial component of the velocity at the inlet will be equal to 20 meter per second. So one thing that we have to keep in mind is that there is one thing called the uh, overall efficiency for the the problem. It's mentioned that there is a overall efficiency that takes into account shaft plus shaft losses in the friction, then the hydraulic losses. So that is called the overall efficiency. If it only takes into account hydraulic losses, that will be called as hydraulic efficiency. So that is the distinguishing parameter. So we have used the hydraulic efficiency to get the power and the head at the inlet. Since this is not an impulse turbine, you can directly use the head at the inlet rather than the kinetic energy. The velocity of the fluid at that velocity of the fluid is the velocity of the fluid at the inlet coming out of the nose from the penstock pipe. So once you have code this, it's very straightforward. Uh, the first part of the problem, you have to determine the guide blade angle. Guide blade angle alpha. So if you look into this problem, uh, this is the alpha. How will you calculate it? We have got CF1, we have got CW1. We just use tan alpha. So tan alpha will be equal to CF1 divided by CW1. That is equal to CF1. It's given as 11.9. We have calculated it. CW1 that is 20. That 0.495 and getting alpha, the guide blade angle will be equal to 30 degrees and 45 minutes. The second part of the problem, we have to calculate the wheel vane angle. Theta. So that is tan theta. Just like the alpha component, you have to determine theta, that will be equal to CF1 divided by CW1 divided by C plate. So that's also straightforward. CF1 divided by CW1 minus C plate. So that is 7.9 divided by 20 minus 3.13, that is 0.705. Theta is equal to tan inverse of 0.705. So that is equal to 35 degree, 11 minutes. So that is the wheel vane angle theta, right vane angle and the wheel vane angle. The third part of the problem, we have to determine the diameter of the wheel at the inlet, and then we have to calculate the width of the wheel at the inlet. How to calculate the diameter of the wheel at the inlet? For that, quite a few things are required, right? We need the velocity, and then we need the flow rate. So we need the velocity actually, and the RPM. So basically, in this case, it's just RPM. For the width, we can calculate everything by flow rates, and the similarly the same process using the shaft efficiency. So diameter of the wheel at the inlet, how we'll calculate diameter of wheel at the inlet D1. So we know the blade velocity. C blade is equal to 5Bn divided by 60 at the inlet. So C blade we have already calculated from the formula that is available. That is equal to 3.13. That will be equal to 5 into diameter into n. N will be 150 divided by 60. That will be D is equal to 0.398 meters. Diameter is equal to 0.398 meters. Then last part of the problem, width of the wheel at the inlet. That's a we can denote it by P1. So how will we tackle this part of the problem? Which all are the available parameters that are present to calculate this one? The only thing that we need here is the flow rate. So once you know the flow rate, we already know the actual velocity at the inlet. Sorry, the flow component of the velocity at the inlet. You multiply it with the area. That is the diameter multiplied by the width of the blade. Area into velocity, flow velocity compound will give the discharge. And that is quite different challenge. Uh, the overall efficiency is given. So from that, we can actually get the shaft power at the outlet, and the denominator will be the same as at the head at the inlet. So what I meant to say is that there is one parameters that is given in the problem. That is the first part of the problem. The overall efficiency of 76%, not the hydraulic efficiency. It's the overall efficiency. So it's pretty similar to that of the hydraulic efficiency, but the only difference is that instead of the power at the top, instead of the hydraulic power, it will be the shaft power at the top. That takes into account the mechanical losses divided by the hydraulic power, the inlet power, water power. You know the head, can calculate that straight away. Shaft power is hydraulic power plus mechanical losses divided by hydraulic power, divided by the inlet power. The hydraulic power to the inlet power is 76%, is 80%. This is 76%. How we get this? The output power is given as 150 kilowatt, and the inlet power is could be written as rho G into Q into H. So rho is just 10,000, it's water. So just cancel out each other. The only unknown, this is H is 8, rho is 10 Q, G is 9.81. Only unknown is Q. So this eta overall is given in the problem as 0.76. So basically overall efficiency is nothing but the hydraulic efficiency multiplied by the mechanical efficiency. The losses associated with the shaft power is also taken into account here. Therefore, Q, the discharge, we can determine as 2.515 meter cube per second. So this is equal to the area, that is equal to the diameter multiplied by the blade width into the velocity, the flow velocity component that is CF1. So from here, we can calculate the blade component. D1 we have already determined from the previous part as 0.398, and CF1 is already given. We have determined as 11.9. Beg your pardon. So basically it's area, right? So as you could see, this is into the plane of the paper, and flow happens in this direction. So this is the diameter D1, the same outside of this one, same D1, and the width is B1. So this can give a better clarity. Both are at the D1, and this distance is in a vertical plane. So the flow happens in a plane, in a direction normal to that vertical plane. So area into velocity will give the flow rate. So area is basically the perimeter into the distance, into the vertical distance. Perimeter is pi into D1, not D1. So there was a small mistake. It is pi into D1. Pi into D1 into B1, that is the area, into CF1 will give the flow velocity component. So from here, B1 will be equal to the flow rate divided by pi D1 into CF1. Just substituting the values that you already calculate, B1 is equal to 0.169 meters. So this was a comparatively difficult numerical compared to the previous one. We had to determine guide blade angle, alpha, wheel angle at the inlet, theta, diameter of the wheel at the inlet, and the width of the wheel. So the given parameters, we know a formula for the peripheral velocity, radial velocity, the turbine rotational speed, and the overall efficiency. So how will we tackle? First we need to determine the guide blade angle. Guide blade angle is alpha. For that will be, if you take tan alpha, CF1 divided by CW1 will give the tan alpha component. So CF1, you can directly calculate the radial flow velocity at the inlet as 0.95 into root of 2 splits. But the other component CF2 will be equal to the actual velocity at the exit, because it's a Francis turbine where the outlet will be purely radial in nature. So we can determine, first of all, we have to determine the flow, the whole component of the velocity at the inlet, CW1. How to get that? We have to use the turbine hydraulic efficiency. In the hydraulic efficiency, just like the previous case, we use the outlet power in terms of C world velocity in the blade velocity divided by GH. The head is given straight away. From there, we can get the world compound. Once you get the world compound, it's very straightforward. You can calculate the guide blade angle, wheel angle at the inlet. Theta is equal to CF1 divided by CW1 minus CB1. Everything is calculated. So blade component velocity is nothing but the peripheral velocities. We got it from this equation. And then the diameter of the wheel at the inlet and the width of the wheel. So diameter of the wheel at the inlet from the blade velocity we have calculated using this equation. We can equate this equation. The value of the peripheral velocity of the blade velocity equal to pi d n divided by 60, and d is the only unknown because n is known. It's 150 rpm. Then you can compute the diameter at the inlet. Once you get the diameter, you need to calculate the width. You have to determine the discharge. Discharge will be equal to pi d into the width of the wheel. That will be area multiplied by the flow component of the velocity CF1 at the inlet. So only a component which we have to determine to obtain the width is the discharge. How to get the discharge? Only using the overall efficiency. Because in the hydraulic efficiency part, we just cancelled out the Q part, rho and Q from the top and the bottom. That's why these are coming such a simplified form. But in actual way, it is rho g QH at the bottom, and top also it's rho g into rho g rho Q into CW1 into CP. In the case of overall efficiency, the only distinguishing factor is that in addition to the hydraulic losses, there is this mechanical losses also coming into picture that has to be reduced from the total head that is available at the inlet. That's why the efficiency reduces from 80% to 76%. So the outlet power is given as 150 kilowatt. That simplifies our problem straight away. This is the mechanical output. The actual mechanical output that is obtained, that is a shaft power that is obtained. So the denominator will be rho GQH, the same as that of this one. The only unknown parameter is Q, and we got it as the only unknown parameter is B. Q from this one, you get Q. And once you get Q, you can calculate B using this area to velocity equation. So that completes question 5. Yes, the question what you have written is right. You have to take into account the head loss. Note the head loss that we have seen in the previous case of the penstock pump. This is the hydraulic losses and the mechanical losses. Hydraulic losses will from the inlet head that gives a hydraulic efficiency. Hydraulic loss and the mechanical losses from the inlet head that gives the uh, mechanical or the overall efficiency. So look into sixth problem. It's a numerical. It's a multiple choice question for identifying the type of turbine used in a hydroelectric power plant. Which type of turbine is used in a hydroelectric power plant having a high head and a lower discharge? Kaplan, Francis, Belton, none of these. High head is a luxury that we can't afford in most cases, but when high head is available and a low discharge is required, yeah, right. Which the answer is Belton turbine. So I'll make a table that distinguishes the three turbines that are available in the options, and that can give a very good idea in which all situations which all turbine is required. So criteria for classification and the three turbines available. Pelton, Francis and Kaplan. First type of turbine. Pelton is an impulse turbine. Francis is inward flow reaction turbine. Kaplan is a propeller as a counterpart of axial flow turbines, axial fans, propeller type turbine. So we have seen what is a reaction turbine. What's a Francis turbine in this case, where the outlet will be only having a flow component. There is no radial component for there is no wall component for the Francis turbine. So to be purely radial in nature, there is no wall component. This is the distinguishing factor for this problem. Head is used for high head, 250 to 1000 meters. So Francis for medium, 40 to 600 meters. And it's used for Kaplan is used for low heads, 10 to 70 meters. And then the other parameters that is available, that is discharge, since this is based on natural height or the head of the height that is available, the potential head that is available, it can produce only low discharge. Low discharge, medium level discharge. Francis is medium in all the cases. Kaplan, high discharge. It requires high discharge because its head is low. It has to compensate everything using the discharge. So rho GQH term. So once head is less, you have to compensate that using the discharge to get sufficient inlet power. Then the other important parameter is the flow direction. Here it's a tangential one. So in the first problem, impulse turbine, we have seen uh, everything. This is in a vertical plane, which is everything is happening tangential to the radius of the blades or the center of the blades, basically the hub. So this happens in a vertical plane, and the radial direction happens to be in a plane perpendicular to the plane of the paper. So everything happens tangential in a plane that is tangential to the uh, radius. So if I try to draw this using a top view, so what I would expect is that this is the radial direction and this is the blade. The entire thing, the three that I have drawn, that is into the plane of the paper. So the fluid comes in this direction, tangential to the radius, and takes a 165-degree deflection and goes in the same plane as well. So in this plane itself, so it won't go out of it. That's why it's a tangential blade. It's called a tangential flow impulse turbine, tangential flow turbines. The second one, it combines both the radial and axial flow, axial flow, and this is purely axial in nature along the axis of the turbine. That's why I meant to say that it's a counterpart to the axial fans that are up there. So here it is, and the most important parameters, energy type, energy conversion. So here it converts potential energy basically kinetic energy, potential energy to kinetic energy to mechanical energy of the shaft. Final form in case of turbines will be mechanical energy. So it converts potential energy to mechanical energy because we consider the head. So it comprises of the actual kinetic energy as well as the pressure part. So both of them converts to the potential energy. So the Kepler turbine uses both kinetic energy and potential energy to mechanical energy. It's a combination of both of them. And efficiency, uh, normally it's about 85%, and here it is 90% and 90%. So that gives an overall idea of what which type of turbine is in which cases, or what kind of input parameters are required for a suitable for an efficient working of uh, one of these turbines. The next question is actually a continuation of uh, next question is actually a continuation of the previous problem. So in the one of the earlier problems, a numerical was there, right? So we have learned something from that. So that will be required in this problem uh, to identify the type of turbine that might be suitable for certain cases. The question is the hydraulic turbine which is suitable for a speed range of 95 to 440 RPM is Pelton wheel, Kaplan, Rankine, Francis. So you need to have an idea for a distinguishing to distinguish these turbines. So what should be the approximate range in which these operates? Basically, you can have a qualitative idea. Specific speed is equal to entropy divided by h raised to 5 by 4. So something which uh, operates at a higher specific speed that has got a higher discharge. Uh, and so what I meant to say is that Pelton turbine operates at a higher head, but its discharge is less. So correspondingly, the speed at which the turbine rotates will be less. But the thing is exactly opposite for Kepler turbine. Its head requirement will be less, but to compensate in the power, it should operate at a higher discharge. So higher discharge corresponds to higher RPM of the turbine. So a higher specific speed uh, is something that you expect with Kaplan turbine, and Pelton will be somewhere lower, and Francis will be somewhere in between. But that doesn't help in this problem where a speed range is given, so 95 to 440. How will we distinguish? How will we say that this is a high range or a medium range or a lower range? So you need to have some kind of an idea in which the turbine operates, the range in which the turbine operates. So I'll give you that. Usually, the impulse turbines like a Pelton uh, operates in the previous problem. We have seen it operates at a higher head from 20 to 250 to 1000 meters, but its specific speed will be specific it will be in the range of 0 to 60 RPM. And then there is this Rankin. Sorry, then there is this reaction turbines. And then there is this reaction turbines with medium range of the specific speed. For example, Francis turbine, which operates somewhere between 60 to 300 RPM. And then there is another kind of uh, reaction turbine called the Kaplan turbine or propeller turbine, which is purely axial in nature, which operates in a very high RPM range. So somewhere around say greater than 300 RPM in all the cases. So the question says, if it was very low, 0 to 60, it would have been impulse. So Pelton wheel is wrong. 300 should be above 300 in all the cases, so it can't operate below 300. So the answer, the Kaplan turbine is wrong. Franklin is additional choice not needed for this problem. So the answer to this problem is Francis turbine. So it can operate from 60 to 300. That is kind of in the vicinity of the problem. The question asked in the problem, in the range that is given in this question. So that completes a set of problems that I have for today. So we have seen a few multiple choice questions and numericals based on the hydrogen power plants and hydroturbines. Basically, how does the power plant works and which all are the main turbines that are available and dimensionless parameters and how to solve problems for impulse turbine and reaction turbines using standard velocity triangles and general classification of the turbines and in which all cases they are used. And finally, problem to distinguish these turbines or the wheels based on the specific. That's all for this week. If you have any questions, you can post it in the forum that is available on the website, course website. We'll meet next week, most probably on Saturday itself, using the next week's lectures.